Thank you for the introduction, and thank you for the invitation. And I'm very glad to talk here, and it's a good chance. So let's get into our talk. So basically, we will first outline the contours of this talk. So in the first part, we will introduce some motivations. So it was also initially defined by Alan Kohn, and which is living now. That this so-called the quantized differential of A, and here F, which would be a unitary self-joint operator, and I, which will be in a system algebra, which will be represented in this hyperspace. And in general, in the setting of noncommutative geometry, we will consider this on a manifold, like many talks in this morning. But for getting some more precise characterization of this quantum differentiability of this quantum differential operator, we would just consider some simple case. For example, in commutative case, we would just consider the d-dimensional torus Td. Well, on this torus, we define this operator F as in this form. Well, D is a Dirac operator. So here F can be understood as a Hilbert transform. And we take A to be the multiplication operator by a function F. So Jensen and Wolf, they have proved that the quantized differential operator d hat F belongs to the Schatten B classes if and only if F is in the Besov spaces BPP d over P on this torus. And recently, there is a first result which concerning the noncommutative case, which concerns the quantum torus T theta D. Well, on this quantum torus, we define this quantum differential operator d hat X as this form. Well, here d hat Xj would be the commutator like this. Here, the curly Q Rj will be defined as a quantum counterpart of the Riesz transform on the quantum torus. So these three authors, Edward MacDonald, Fedor Sukhchev, and Xiong Zhao, they proved that this quantum differential operator belongs to the weak Schatten P classes SD infinity, if and only if X is in the Sobolev spaces on this quantum torus. So our goal of this talk is to extend, for example, this classical case to the noncommutative setting, more precisely on the quantum tori, And this is, to some extent, is also some kind of refining of their results. We will characterize the strict Schatten property of this quantum differential operator. So let's begin to introduce some setting. First of all, our basic setting is noncommutative tori. So given D unitaries, U1 to UD, they satisfy the following commutation relation. Here you can see theta Kj is the metric centris of this Riesz symmetric matrix. And we take A theta to be the universal system algebra generated by these D generators, U1 to UD. And in this universal system algebra, we would define the monomial U power m to be U1 power m1 times UD power md. And here, the polynomial would just be a linear combination of this monomial and yes, this polynomial will be our finite sum. Sorry. Okay, so we got this kind of polynomial, so we can got a polynomial algebra, and this will be a dense subalgebra of a theta, and we define a trace on this polynomial by tau x equals to alpha 0, which would be just the coefficients of the u power 0. And since this polynomial algebra is dense, so tau can be extended to a faithful tracial state of this universal theta algebra A theta. And we take the GNS representation of this tau, then take this Weierstrass closure of this A theta. So we could get a polynomial algebra T theta D, which will be denoted as the quantum tori. And the noncommutative empty spaces on these quantum tories will be quite standard, just by using the standard definition of this noncommutative empty space. And so for some special case, if X is in the L2, so just by some standard, something like Planck-Scherel formula, we can get this form by something like a Fourier series. And here, the coefficients can be, here the norm can be computed by the coefficients. So, on this L2 of T theta D, we define the Fourier multiplier. For example, given a function G, we define the Fourier multiplier with simple G to be Tg x on x is just the multiplication of Gn before the coefficients of this Fourier series. And two quite classical examples would be the Besov and Riesz potentials. Here we take this simple function G to be J alpha and I alpha. Well, J alpha and I alpha will be defined like this. So the corresponding Fourier multiplier on these quantum torus will be the Besov and Riesz potentials. And next, we will define the partial differential operators, partial J, on these quantum torus. And here we can we know that we only need to define this only on this monomial u power n, and this we could see that this is also a kind of multipliers, and this will be just be a simple function. And with this partial differential operator, we can define the Laplacian, or just like in the classical case. Then we can write it in the other form, like this. So we could see from that minus delta is a positive operator on this L2 of T theta D. And we define a bigger dj to be minus I partial j, which is then self-adjoint. Then given a multiple indices into this n0d, and which means its n1 to nd can be 0, then we can define the multiple derivation operator d power n, and then it's defined to be d1 n1 times to dd nd. So we make a convention that in the following, in the sequel, we would just consider a special type of multiplier. For example, we give a function phi on Rd exclude 0, such that phi is homogeneous of order 0. And we made a convention that phi 0 equals to 0. Then we call the Fourier multiplier with this function phi to be the Calderon-Zygmund transform on quantum tori. So there are still many examples of this. Like if we take phi C to be psi j over the module of psi for j between 1 and d, then we could see that this is just a quantum counterpart of the classical Riesz transform, and which we have already defined by Rj, and we see that the Schwarz space on this quantum torus is defined to be the subset of all these x in the quantum torus with the sequence of Fourier coefficients which has rapid decay, which means the sequence of these Fourier series coefficients can be dominated by the reciprocal of any polynomial. Then we take it due to be the space of to be distribution space on quantum torus, and which will be defined by S prime of T theta d.
But it's a wrong notation to use x belongs to T theta d. I mean, this is a standard definition of C infinity of T theta d. T theta d is compact, so there is no Schwarz condition. It's C infinity. That's the definition which I had in my contract note in 1980.
Yes, but here we take the Weak-Star closure.
Weak-Star closure?
Yeah.
If the Fourier coefficients are decaying, are of rapid decay, it is not in the Weak-Star closure, it's in the C-star. What are you saying?
No, I mean, for the definition of the quantum torus, we'll take a Weak-Star closure of this GNS representation.
Yeah, but I mean, if the Fourier coefficients are of rapid decay, it's not in the Weak-Star closure, it is in the C-star.
Okay, yeah, so you mean here?
Yeah. If this sequence is of rapid decay, you are in the C-star algebra, you are not in the Weak-Star closure. You are obviously in the norm closure of finite polynomials, so you are in the C-star algebra. You are not in the Weak-Star closure.
Yeah, but anyway, it will be a subset of this quantum torus, right?
I don't understand what you're doing.
It's just a notation difference. Either you think of the Fourier coefficients and then it is Schwarz.
I mean, if you take the fundamental algebra of the quantum torus, okay, and if you take the things there whose Fourier coefficients are of rapid decay, you are not in the fundamental algebra, you are in the C-star algebra.
Well, you are in the fundamental algebra.
Yes, but it's still in the.
Yeah, but why do you give a new definition? I mean, this is a 42 years old definition. Okay, please keep going.
Sorry.
Okay, so with this distribution space, we will define the Besov space. Mm-hmm. So we take phi to be the Schwarz function on Rd, and here this will be the quite standard Littlewood-Paley decomposition. And we denote phi sub k to be the inverse Fourier transform of phi 2 power minus k times some variable. So we define the Besov norm for x in this distribution space. Mm-hmm. Like the Besov norm for x is defined to be the sum of this 2 power q k alpha times this phi k convolution with x, the p norm of this power q.
Okay, that's do something.
Yes, yes, and there is a pair of equivalent definitions of these Besov spaces, but here this will be convenient for us, and we'll choose this one to work with. And so we define the Besov space associated with the quantum torus to be all these x in this distribution space with a finite Besov norm. And after all these settings, we will consider the main objects of this talk, which could be the commutators of the Calderon-Zygmund transforms. For A belongs to, for phi belongs to this C infinity of this only d-dimensional sphere, and this phi will just be, since we have made a convention that this phi will just be the homogeneous function on this on this td, so we on this rd, so which can be considered as a function on this d-dimensional sphere, and we define mx to be the multiplication operator by an elements x in this quantum torus. Then we define a commutator of t phi and mx.
Yeah, so I mean, from the start, I mean, you could have said, okay, I take the 2-1 factor from the quantum torus. I have my Calderon-Zygmund. I have my operators t sub phi, and I take this commutator. I mean, this is exactly the same.
Yeah. Yeah, like we have defined commutator of this Calderon-Zygmund transforms. And so, like we have mentioned in the beginning of the talk, we want to characterize these Schatten properties of these commutators.
Okay.
So basically, we got two directions. The first one is this Schatten p-norm of these commutators controlled by this Besov norm of this x. And the second direction is that the Besov norm of this x controlled by this Schatten p-norm of this commutator. So for the first direction, we will use quite standard tools like the interpolation. So we want to get these estimates on some endpoints. So first of all, we will get our estimates on the endpoints p equals to infinity. Well, so without too many surprise, yes, basically our strategy is to realize these commutators by a operator on this L2 of ZD, since we got this expansion of this. Yeah, since we got this expansion of this x belongs to L2 of T theta d. And attention, here we need that alpha plus beta minus than 1. So here our case cannot cover the case where alpha equals to beta equals to 0. So in this case, corresponding to the classical case, this will be characterized by the BMO norm. But here unfortunately, we do know which BMO norm will be appropriate for us to control this operator norm of this commutator in this quantum torus.
You mean you don't have an analog of the oscillation of the mean oscillation?
Yeah.
Yeah, I see. Okay.
And second part is for the endpoint p equals to 2. And here, yeah, it's a much simpler case, which can be done by some standard tools like Lagrange formula and many things and etc. And last part is for p equals to 1. So notice that we didn't get directly the form of this Besov norm, where we just get the 1 of x. But so for sure, if we just take this x, this x belongs to this this distribution space. With this assumption, this part of this x of these Fourier coefficients is contained on this intersection of this bar with ZD, we could get the estimate on every segment, like on on every segment, since we define this Besov norm by the little pair decomposition. So it will still recover the estimates of the Besov norm when p equals to 1. And with these three endpoint case, we use the complex interpolation to obtain the general case for p. But you may be wondering why we got three endpoints, 1 to infinity. It may be strange, but here you may notice that here alpha beta, we need alpha beta be bigger than minus d over 2. So, like if you just do this interpolation for the endpoint of p equals to 1, and p equals to infinity, the index in the interpolation might not fulfill the conditions of this alpha beta. So we need to divide it into two parts. The first part 1 and 2, and the second part 2 and infinity. So with this we conclude the first direction.
And what if you do real interpolation? What if you do the Lyon's real interpolation? Then you should obtain, this double index, the Schatten class with double index.
Yeah. I have not tried yet, so yeah, I don't have some precise idea.
Okay.
So next here is to deduce the converse estimates of the Schatten estimates of these commutators. Yeah, but firstly, it will be more complicated than the previous direction. So, first of all, we will introduce some other point of view of these commutator. Like, back to the introduction. Here, we can see that we can associate to ZD a representation to this commutator T theta D just by mapping, for example, n to u by mapping m to u power m. Then, with this commutation relation, we could compute something like um times un. Then we could get, but so attention here. This is not the representation. This would be a twisted representation, since there would be some coefficients before these terms. So we will define T theta D to be the twisted fundamental algebra of ZD and sigma, where sigma will be in this form, and I will not calculate in detail. And the theta we have already seen in the definition of commutator. And we define 2k times T theta D to be the twisted fundamental algebra over this group 2 power minus k times ZD, and with the 2 cocycle sigma k. And sigma k is a 2 cocycle induced by sigma on these products of groups. So yeah, so here is our theorem. We got a similar result for this, just like in the previous result, in this dilated commutator 2 power k times T theta D, where before that there is another coefficient And with this, so first of all, we will introduce some multiplier result. Like we define a function omega k c to be like this. Well, if you just observe it carefully, it will be just like some sort of the Riemann sum of the integral. Just like in the following. Yes, you could see that in the following corollary, we got a function omega c defined by this integral. And you could see that this will just be the Riemann sum of this integral. So why are we using this discreted version of this integral? So we observe that this omega is homogeneous since phi is homogeneous. Well, but we cannot get directly through the form of omega like this. So we use the Riemann sum of the omega by omega k. Then we could get we could get that the omega k is a Fourier multiplier on this Besov spaces, on this dilated quantum torus. And with that, since we know omega k is the Riemann sum of this omega, then in this inequality we take k to infinity, then we can get this inequality. So here, one basic strategy to deduce the converse direction is to use another multiplier like t omega minus 1 to eliminate this t omega. So for the next lemma, it's just dedicated to prove that omega minus 1 is exactly a Fourier multiplier. And so here we could see that why we are making so much efforts to make sure that omega is homogeneous. Since we define the Besov norm by the decomposition, so it will be defined by segments. And if we see that omega is homogeneous, then we need only to ensure omega is a Fourier multiplier on one segment. Then we can just extend it to arbitrary segments, so which ensures some sort of the uniform Fourier multiplier. So with this, we could obtain that omega minus 1 is a Fourier multiplier. And so after that, roughly, we take t omega minus 1 acts on this t omega of x. Then we could get this inverse result, this inverse inequality. So combining these two estimates, and the previous one, we can say that our commutators of Calderon-Zygmund transform will be in the short mid classes if and only if x is in the Besov spaces, so which extend the classical case. And here our multipliers can be arbitrary, will not just be the Riesz transform. And after that, we will calculate a related trace formula. So to calculate the trace formula is to engage the theory of pseudo differential operator on the quantum tori. And so first of all, we will introduce the symbol So we define class Sm of Rd to this short space. Well, this class consists of all functions or maps low belongs to this C infinity of Rd to the short space, and which satisfies this condition. And since this satisfies this condition, we can endure it with a semi-norm. So, but the important case is a homogeneous class. So we define a homogeneous class of these symbols S prime M of Rd to the short space, and it will consist of all these maps low still in the C infinity, but here low is homogeneous with order M. And we mentioned that if there exists another homogeneous symbols low M minus J belongs to the M minus J class, which satisfies these following situations. And these following situations is meaning that after low minus 1, this sum is still in the in the previous definition, it's still in this class Sm. And so we just take the first term. For example, we take j equals to 0, then we get low m. Then low m, which will be the first term, then will be called the principal symbol of low. And here is our trace formula. Still, like our convention for phi is a homogeneous function of order 0, then we get the following trace formula. So, how to calculate this? So the basic strategy is to using the simple calculation of these commutators and engaging Kahn's trace formula on quantum towers. So let us define a little bit of the pseudo differential operator. So we define a group of alpha s, parameter group of alpha s on this monomial u power n to be like this, and we let p though to be the pseudo differential operator, sending a in this short space to be defined as this integral. Well, this integral is not converged in the sense of norm, and it is an oscillated integral. Well, for some special case, if A admits this expansion, then we could get that P though of A will be just this finite sum, this sum, and which means that for this A in this short space, we need to only decide the value of low on ZD to determine the value of the pseudo differential operator on A. And so, with this, we will introduce the following trace formula obtained by these three authors, Edward MacDonald, Fedor Sukhchev, and Dmitry Zeng. They have proved the following trace formula in the quantum theory. So basically, this means that to deduce this trace of this operator, we need to calculate the symbol of this operator A, this self-adjoint operator A. So we will give a sketch of the proof of our trace formula. So first of all, like we said, is to calculate the symbol of this commutator. And so the symbol of this mx t phi is low c times x, and the symbol of this t phi times mx is expanded as this. Well, there's nothing else. It's just like the binomial theorem. You see. And by the homogeneity of this function phi, we could see that the symbol of this commutator, the order of the symbol of the commutator is -1, and leading term is being like this. So here, so naively or intuitively, we want to construct an operator A, which has the same symbol with this commutator. So intuitively, we would just like to use this. And while here is a theta, here is a c, since the operator is the module of A times 1 minus theta. So the symbol of theta is c. So intuitively, it's using this, but remember that A need to be self-adjoint. So actually, A will be not in this form. So we need to modify it to get a self-adjoint version of this A. So if we admit this, we could get a self-adjoint operator A, such that this modulo of A times 1 minus theta admits the same principal symbol with these commutators. Then we obtain that they got the same trace, and here actually is not so obvious. We need to manipulate a little bit. Like, so basically, since they got the same principal symbol, then we could say that the power d of these commutators minus this one, they will be eventually they will be in S1, yeah, in S1. So
you should have said at some point that phi was a singular trace. It is a Dixmuir trace, phi.
Yeah. So phi is a Dixmuir trace. So eventually the difference of this term will be in the S1. So S1 will vanish in this Dixmuir trace. So we could obtain that they got the same trace. So after that, by engaging the previous trace formula, we could calculate the trace of phi of these commutators. And I think I will finish here on my talk. Thank you.
Thank you. Are there any questions?
No, I don't want to insist on that, but you see, I mean, for the notations, you should look at my Contrandu note of 1980, where I was defining C infinity, and I was also defining the pseudo-differential calculus for the noncommutative torus. Yeah, there is no point to redefine it. I mean, you know, it's already there, and it was very well done by Saad Baj then in a more general setup. I mean, I don't know if you know this Contrandu note of the 1980s about non-commutative differential geometry.
Not too much.
No, not too much.
Since I already mentioned that, we only consider some like the most simple case. We just consider the torus. Where
okay. This note is about the non-commutative torus. So it's,
I mean it's a more general setting.
I don't like to say such things, but when I see a definition for something which I know since 40 years, I mean, you know, I'm tempted to interfere.
Is there any other question?
Well, yes, I also want to say, you know, it's quite good to have these interpolation results because they are quite useful. But then you should use also, as I said, the real interpolation, because then you can get more, for the boundary case, for instance, you have this L1 infinity with two indices. And the 1 infinity is really the domain of the Dixmuir trace. So but for that, you need a real interpolation. not complex interpolation.
Yes, yes. I think this is also another problem that we're considering now.
Yes, because this should be done with real interpolation. Yeah. Otherwise, you are missing the natural domain of the Dix matrix.
Yeah, like we said,
yes.
For example, in the beginning. Yeah. Okay.
Because the Besov space,
yes,
they have also this property.
Yes. Yes. Something like this.
Yeah, exactly.
Here, here's only the Riesz transform. So now we're considering. So can we replace it similarly by a more general Calderon-Zygmund operator?
Yes.
So this will be engaged this kind of problem.
Yeah. Okay. Very good. Okay. That's quite good. It's quite important to do these estimates very carefully for the quantum theory. No. But we prefer to call it non-commutative torus rather than quantum. It's a question of, the word quantum is very often overused. I mean, there are many things which are called quantum. But,
it's short term.
Well, it's short term, yes. But I remember somebody. I don't want to be. Can you cut the camera? Can you cut the camera? I remember somebody saying, these quantum groups, which are neither quantum nor groups. They are perfectly fine. But it's a little bit. What I mean is that, they are really non-commutative tori. That's what they are. Quantum, why are they more quantum than the ordinary torus? This is totally unclear. You see, I mean, there is no reason. They are just non-commutative tori. That's all.
Okay, so thank you. So now we have a coffee break.
Okay.
20 minutes.